All right, we are now recording. Let me get set up from the current slide. Yes, ma'am. I can't hear you. Your first quiz, what about it? Okay. What's the question again? Okay. I wish I would have already given them back, but I've still got 1, 2, 3, 4, 5. Yeah, oh, anytime, yeah. If you want to come by, stop right after class or whenever. Yeah, you can always, any of you can see your quizzes, tests, everything. Everything's been graded, but I've still got several people who haven't turned in stuff, and that's what I'm saying. If I can find out if they're withdrawing or not, see, if I return things and then they come and turn them in, I don't know if they've seen, that thing by, somebody else. Oh, look at this, a paper coming in. Oh, okay, great, thank you. Wow. Right there, we doubled our input of papers. Okay, I only had 2 before, now I have 4. Wow, my biggest, and of course my best class, and I've only got 4 papers in.
Wait, so
what's wrong with this picture, huh?
if you turn it in on coming up Thursday, we'll still
I'm sorry?
If you turn it in, she did not mean to ask that.
What's that? I need to hear it, I think, okay?
I was going to say, if we turn it in on Thursday, we would still get like the +1 or whatever.
You get your last little bonus point there. Yes, absolutely. Excuse me. What's that?
You want to be my advisor?
I'm going to be your advisor.
You can, okay.
Oh, okay.
Okay, you can be.
Okay. Where did that come from?
No, my advisor.
Oh, okay, yeah, I can advise just about anybody. Okay. All right, we just had a slug of new people come in the U.S. system. That means a mass of new people who came in. Okay, Cameron's here. Jake's here. Oh, 10 o'clock scholar, huh? All right. Christian's here. Michaela's here. Okay, anyone else whose name I didn't just name? Okay, let me count again because that was several. 3, 6, 8, 10, 12, 14, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Got it. All right. Sort of stole my thunder there. I was going to start harping on how many papers I was still missing. I'll still harp on it, but we got 4 in now out of a class of 37, but now some of those have dropped or never showed or whatever. But that's a paltry number. And remind you that, as already was mentioned today, Friday is the last day to turn it in once JT is here, and still get your last little bonus point, okay? I will accept them next week, but after next week you start losing points. Next week, if I get them in, you just get your score, and then the following week, or anytime after next week, you start losing points when they come in. In fact, after the last day of class, which is Thursday, a week away, if you turn it in Friday, you'll be losing points. So please get them in, preferably this week, definitely next week. Okay. Now, the comment also came up about the first quiz. I still have an amazing number of blanks on this. It's not that many, but 1, 2, 3, 4, 5. Now, some of those may have, no, maybe only 4, okay? I don't know if those people are coming anymore. I know they haven't been here in a long time. I don't know if they're going to rush in and say, oh, I've been sick and I need to catch up and stuff like this. So I can't return quizzes until, people have either withdrawn or I know they're not going to come back anymore. But I will return them to you next week before the final. After that, it's too late to turn anything in. Now, test 1 excuse me, test 1, there are a few more blanks here. Now some of these are because you haven't taken the test, and others are because I'm not sure if you're through with the test. So if you see a blank there by your name under test 1, and you thought you had already completed it, please let me know and I'll let you see the score. And if you're happy with that, then that's the score you'll get. If you're not happy with it, I'll let you go on and finish the test, because I didn't put scores down for people who were, I wasn't sure were through. Okay, why can I not? There's Skylar. Okay. All right, good deal. Then quiz 2, I don't think I've quite got half of those in yet. And guess what, folks? The test is Thursday. Okay. Chapter 2 test. We are that close to finishing it. I thought we might finish last time, but we didn't quite. So we're going to finish it today, and the test will be Thursday. Okay? So, I can't think of any other announcement type things. Please get the stuff caught up. And if you know of anyone who you know has not been here for a while but started in the class, get with them and say, hey, you need to withdraw from this class, or you need to get your stuff caught up right away. Okay? Because after I've returned stuff, too late then. All right. Now, we have done example 3, long time passing. Okay? The next topic is slant asymptotes, which we're not going to do. Let me see if I can. This is better. Okay. They did not have example 4, example 5, or example 6 in the book. In the slide set. So that's what where we're going to start today is example 6. We've done 4 and 5, 3, 4, and 5, but we haven't done example 6. Any questions before I get started? There have been a few questions today, all excellent. Any additional questions? Sometimes they block it from the outside and I don't know that. Okay. No questions? All right. Example 6. Let me get my pen set up. All right. Sketch the graph of f of x is equal to, okay, x squared minus 9 over x squared minus 2x minus 3. All right. What's our first step? I know it's... Okay? We're taking baby steps. Okay. No. What's the first step? Well. Second? Okay, what's? Factor everything in sight. Okay? Now, what are a couple reasons for that? Anyone tell me why we would want to factor? Evan got it. Okay. Anyone let me know why we would want to factor it? Sounds good? No, what do you say? Okay, absolutely. We're going to find zeros in the numerator. Those are going to be our horizontal asymptotes. Not horizontal asymptotes. They're the zeros of the function, the x-intercepts. Okay. We'll also find the vertical asymptotes. Yeah, 2 big reasons to factor there. The third one, though, is probably just about as important. What if you had any common factors? You need to eliminate those, because if there are common factors, that's not going to be a vertical asymptote. That's not going to be a zero of the function. Okay? So we need to also look for that. So let's factor that numerator. Can anyone do that off the cuff? X plus 3 times x minus 3. Okay. In that denominator, we don't know that it's going to factor, but we hope it will. If it will factor, what's going to be the first factor in each of those two, first term? Second, x times x. Very good. Okay, and then what will be your signs? Second? X, you said minus 1 or plus 1? Plus 1 and minus 3. Sounds like a winner to me. Let's see if that works. X times x is x squared. Got it. X times minus 3 is minus 3x. Plus x is minus 2x. And then minus 3. Perfect. And what do you notice you have here? Second? X minus 3's are common factors. Even though we eliminate them here, we still put a comma here, and we say x cannot equal what? 3, or, and we can go on and put it, what else is in the denominator? Second? Second? Negative 1, okay. Y'all are talking so softly. Okay. All right. So x can equal 3, and it can equal negative 1. One of those is going to be a vertical asymptote. One is not. Which is going to be your vertical asymptote? Anybody? The minus 1 is your vertical asymptote. The 3 is going to be what? A hole in the graph. Okay? Because that's eliminated here, but you still can't be 3. Okay? So that gives us a really good start for our graph. It says sketch a graph. We've already know some information. So what are some other things you can tell me based on what we got left? We only got 2 factors, one in the numerator, one in the denominator. What do they tell you? There's 4 things we look for. Okay? Actually 5, we already got one. Holes in the graph, we got that, okay? And we already have another one. You just told me, what was that? What 4 things we look for?
We just did the vertical.
Okay, vertical asymptote. We just said it, and what is it? Okay, x cannot equal negative 1. Perfect. And if you want to do hole in the graph, so I'm going to do a hole. I don't usually do this. The hole is going to be x cannot equal 3, okay? I don't usually put that down, but I will this time just because it's fun. Okay. And here's Ashley. All right. So we got one of the 4 things, vertical asymptote. What's another one? Help me, folks. 4 issues we look for. Vertical asymptote is 1. Horizontal asymptote. What in the world would that be? Where do we go to find that? Anybody? Horizontal asymptote. What do we look for to find the horizontal asymptote? Anybody? Help me. Say again. Horizontal asymptote. Horizontal asymptotes are telling you what's happening in the long run, way out there, when x is very large positive or very large negative. What's going to dominate out there? The leading coefficients, or the ratio of the leading terms. And the leading terms here are x squared over x squared. What's that ratio? 1. And this is y is equal to 1. There is your horizontal asymptote. Y is equal to 1. Okay? What's the difference between vertical asymptotes and horizontal asymptotes? I know verticals are vertical, horizontal are horizontal. I know that part. But what's the other thing that's different about it? Can the function ever touch or cross a vertical asymptote? Never. How about horizontal asymptote? Sure. It's just where the function's heading in the long run. For very large. And here's the metric. Sneaking up. Okay. All right. So there's 2 of my 4 things I usually look for. We have the fun fifth one, which is the hole in the graph, which we've already said. What's another one? Say again? Okay, x-intercept, is that what you said? Okay, x-intercept. Okay, what tells you your x-intercepts? Where? What's true? X-intercept is where? Y is equal to 0. Okay? Now, what's your y? F of x. And when can that f of x ever be 0? Only time it is, because this is a rational function, remember? It's only 0 when that numerator is 0. That was the other reason we factored, to see what the zeros were of the numerator. But what does that tell you the x-intercept will be? Say again? Did someone say? Negative 3, 0. And a point is always an ordered pair when you're in two space, which we are. And we already said where y is equal to 0. Well, there's a 0 for the y, negative 3 for the x. One last thing we're missing, and what's that? One of the easiest one to do. Y-intercept. What's true about y-intercept? Where x is equal to 0. And that is by far the easiest one to do. Surprised it took us this long to get there. When x is equal to 0, all these x's are now zeros, and what are you left with? Y is equal to? Say again? What did you say? 3. Negative 9 over negative 3. Because if that's 0, that's 0, and that's 0, all you have is the ratio of your constant terms. 3. Y is equal to 3. X equals 0, that's the first part of the ordered pair. Y is equal to 3 is the second part. So 0, 3. All right, folks? We have, I think, in this problem, everything we need to know to graph this function. We'll see if we do. I hope it is. Okay? I don't think we're going to need a single test interval. We'll see. Okay, let me just tick off a few points here. Okay, what you want to plot first? You got four choices here. That hole in the graph, you really can't do much with that yet. We'll get there later. 4 choices. Which you want to graph first? Somebody, help me. Excuse me. What you want to graph first? The which? X-intercept. Okay. Let me get Reggie here first. Well, he's already here. Okay. All right. Let me mark it first. Okay? So, x-intercept. And what did we say it was?
Negative 3, 0.
Okay, how do I plot that? Left 3, and right there, there's your x-intercept, negative 3, 0. Okay, got it. That's point right there. Next? Anybody?
Do the y.
Y-intercept. Is that what you mean, y-intercept? Okay. And what is it? 0, 3, how do we do that one? Okay, up from the origin 3 times. Just don't say up. Okay, never mind. Okay. And that is 0, 3. Okay. There that one is. 2 other things we can plot very easily. What are those? Help me, people. Hint, I'm going to change my pen to red. Your asymptotes, which one you want to do first? Horizontal one first. And what's the horizontal asymptote? Second? Okay, that's a number. Y is equal to 1. Okay, that makes it an asymptote. It has to be an equation, and there it is. Y is equal to 1. All along there, there's your horizontal asymptote. Y is equal to 1. Okay? And what are we left with? And vertical asymptote, what's that? Cannot equal negative 1. Well, there it is. Okay? That's one reason it's red. You can't touch there. You can touch the horizontal, but not the vertical. So this is what I call x is not equal to minus 1. Okay? Like I said, I think we plotted we got it ready to plot right now. And here's why I say that. Okay? I'm going to change back to black. We have a point in this quadrant. It can't leave that quadrant, can it? Okay? Because in the long run, it's approaching the horizontal asymptote, and it cannot even touch the vertical asymptote. It's stuck right there. Stuck right there. Okay? And this point up here is up in this one. As you go toward -1, it goes to positive infinity. It can't cross it. It can't cross the x-axis. That would make another x-intercept. Okay? And then it heads down toward the horizontal asymptote with one problem. What's that? That one other thing that we didn't deal with. X cannot equal 3. So there's 1, 2, 3. And wherever that would turn out here, when you get above 3, put a hole there and then continue trucking. Okay? There's your graph. Okay? Has all the features here. A lot of times you won't be this lucky that you have everything that you need. But since this one is down in this quadrant of your asymptotes, it has to be approaching horizontal in the long run and approaching vertical as it gets close to it. It never can touch it. And this one has to be approaching vertical. Why can't this one be going down this way? Why couldn't that be approaching this way? If it did, bing! Did you hear that? It just hit the x-axis. And it can't, because we know there's only that one x-intercept. Only one. No other places where y can be 0. Okay? So no, it has to be going up, and then in the long run, it's going to the horizontal asymptote. Okay. We don't know for absolute certain that's what we got, but it's a really good idea. See, this isn't going to happen with this function, I can just tell you that. It could come along and do this kind of stuff all day long. We just get closer and closer to the horizontal. And it could do this thing too, like this, and get closer and closer. It doesn't. There's not enough variation in here. It's just a real simple function. So it's going to be a hyperbola. Any questions? Yes?
How did you figure out 3 was your whole non-negative number?
Okay. Because we canceled out the 3's.
Okay,
We canceled out the factor.
You always have something that'll cancel out.
That's going to be the whole. If you have a factor that's common to numerator and denominator, that will produce a hole in the graph. If you can't eliminate that, that's going to be a vertical asymptote. I mean, vertical asymptote. What's that?
Will there always be a hole?
No. That could have easily been something that you would have factored as x plus 1 times x minus 4. Then there would have been no holes. You would have had 2 zeros here. You would have had 2 vertical asymptotes there. Yes. Yes.
With the hole in the graph, did you go to the right 3 times from the origin of the
right.
asymptote? Or the
1, 2. Oh, I did it wrong, didn't I? Why did you do that? Huh? No, okay, thank you. I was miscounted. Okay, sorry about that. I put the hole in the wrong place. Ew. Okay, get that corrected here. Thank you. Okay, 1, 2, 3. There's my hole somewhere about here. So it's approaching here and there. Okay. Now, if you wanted the exact location of that, just pretend that 3 could be a value and just put a x equals 3 here. 6 divided by 4, that would be 3/2. And that would be right here. So I've got it a little low. So that's one way you can specifically identify where the hole is at 6. But it's not there. That's where it's not. Where the woozle wasn't, if any of you are Winnie the Pooh fans. But never mind. That's way too young for you. Okay. Bless you. All right. Any questions about that? Okay. They do some test intervals. Why? We've already got everything we needed in this one. You won't always. Sometimes you will need 1, 2, maybe 3 or 4 test intervals. If you're going to do test intervals on this, you do one to the left of -3, something between -3 and -1, something to the right of -1, between -1 and, I don't think you need it there, but probably that 3, and something to the right of 3. You really don't need that many, but you could do as many test points as you want to. You'll find they really fit on that graph well. Good deal. Any questions? All right. The next topic here, all right, to move on. Okay, the next topic here is slant asymptotes, which we're not doing. Just to give you an idea about it, here's where those come into play. The only time they come into play. And they're really, only if you just are interested in doing them. Anytime the degree of the numerator is exactly 1 more than the degree of the denominator, you'll have a slant asymptote. Okay? How do you find what it is? Do a division. Okay? Do a division. This one you could use synthetic division. Not all of them you could, but some you could. Do a division and see what your quotient is. Okay? Remember we did this. When you do that division, you'll wind up with a line here, x minus 2. That is your slant asymptote. Okay? Then this part is your remainder. You don't do a thing with it. The thing is x minus 2. So that would be, if this is your origin here, you go down and intersect at -2 and you have a slope of 1. There's your slant asymptote. Everything else then fits one side or the other. It's a lot like a horizontal asymptote, only it's not horizontal. It's slanted. Okay? Already you know, what's your vertical asymptote? Say again? What's your vertical asymptote? X can't equal -1, right? X can't equal -1, okay? So here's one. We're not going to do it, but you tell me the procedure. What would you do? Actually, what you would do is first see if you can factor this, which you can't. Make sure that's not a factor up here. If it is a factor up here, you don't have a slant asymptote. You have a hole in the graph. But it won't be. This will be x minus 2 times x plus 1. So yeah, that will still work. So forget about that for now. What would you do first to find that slant asymptote? Divide. Say again? Yeah. Divide x minus 1 into that thing, and you can do it with synthetic division. Find out what your quotient is. The quotient gives you a linear function. That line is your slant asymptote. Okay, it's pretty easy stuff, but the course description doesn't require it, so I'm not going to do it, but I did tell you how to do it. You do factor to recognize the x-intercepts, okay? You always want to factor. Like I said, there's several reasons to do so, okay? You use long division. You don't have to use long division. You can use synthetic division, okay? But you get, and this time you don't get a term, you just get x. That means that slant asymptote is going right through the origin with a slope of 1, okay? The y-intercept is 0, 2. Just x equals 0, you get y is equal to 2, okay? The x-intercept, we already noted, were, right here when you factored, x equal 2 and x equal -1, okay? So x equal -1, 0, -1, 0, and 2 zeros, those are your x-intercepts. Your vertical asymptote, x cannot equal 1, because it's 0 in the denominator. And then the last part is that waltz here. Okay. All right. Slant asymptote, y is equal to x, because that was your quotient when you did your division. And you plot that as well. They say some test intervals. I don't think you really need them, because as soon as you plot the points you knew, the x-intercept here, the y-intercept here, the x-intercept here, okay? Your vertical asymptote, your slant asymptote, you got points in here, approaching the vertical asymptote that way, slant asymptote that way, slant asymptote vertical asymptote this way, slant asymptote that way. Again, the slant asymptote is like a horizontal. It's where the function's going in the long run. Okay? So you didn't need any test points. It's okay to do them just to confirm what you were thinking, but it wasn't necessary. Okay? Any questions? You're not responsible for slant asymptotes, but just to show you how to do them. If you ever wondered, how did they come up with a function like that? That's how you do it. And that's also a hyperbola, by the way, if you remember that term. All right, applications. Okay, I forgot about applications. We do have some applications here. There are many examples of asymptotic behavior in real life. Okay, for instance, example 8 shows how vertical asymptote can help you analyze the cost of removing pollutants from smokestack emissions. Oh, wow, I didn't know we do that in this course, okay? Here's example 8. A utility company burns coal to generate electricity. Not a great idea these days, okay? The cost C in dollars of removing P% of the smokestack pollutants is given by, C is equal to 80,000 P divided by 100 minus P. And, of course, P is some number between 0 and 100. Okay? Could equal 0. That's not a very good removal system if you're not removing any of it, but it can't be 100, okay, because you can never remove 100%, okay? You're a member of the state legislature considering a law that would require utility companies to remove 90% of the pollutants from their smokestack emissions, okay? The current law requires 85% removal. How much additional cost would the utility company incur as a result of the new law? Okay? There is absolutely no need for you to analyze an asymptote at all. You just plug it in. That's all they're asking you to do. So it's a good example, but it's not really pertinent, okay? All you have to do is plug in 90 and plug in 85, okay? And see what additional cost would do. So here's what they do. They plug in 85. This is what it's currently costing you to remove 85% of the pollutants. $453,333. That's when you're removing 85%, according to this formula. Then, if you're going to remove 90%, you plug in 90 rather than 85. And that gives you $720,000. Okay? Now, for that 5% of the emissions, is that worth it? Now, that's the question for a state legislature. Okay? Let me just give you some examples. If you had the medical field has determined that you will reduce your asthma rates by 5% by going from 85 to 90%. I'm just making up this number. Then what you could do is see how much it costs to treat that additional 5% and see, is it this much? Okay? It's hard, it's terrible to quantify people's misery in dollars, okay? If you want to eliminate those people's asthma, then go on to 90, okay, no matter what the cost. But if you're going strictly by cost and you're going to spend, and maybe it's even that company's workers lost revenue and stuff like this, if they're getting sick more often because of that extra 5%, they may say, hey, this is a small price to pay to keep those people at work, okay? If there's that much difference. But more likely, the whole community. And if a lot of difference, if there's hardly any change in respiratory infections and things like this, then this may not be worth it. But if that produces a significant reduction, then this would be worth it, okay? But tell the company that, no, they'll fight it tooth and nail, okay? They want to keep their profits up. But, sorry, if any of you are in coal industries, I don't want to be knocking on any icons there. But there was absolutely no need for a vertical asymptote in this problem. They said this was it. Now, so the new law would require utility companies to spend an additional $266,667. And since they probably didn't like spending the $453,333 to begin with, they sure aren't going to appreciate that. But if it can be shown medically, that's going to improve the cost to the whole system, you know, then that might be worth it. I think it would be, but whatever. See, they never use an asymptote in that problem at all, okay? Sure, you could have, but there was no need to. So that wasn't a particularly good example for this case, but I wish they had shown the graph, but they don't. It is in your book. The asymptote does show, for those who don't have books, let me point it out to you. It's kind of what I was trying to talk about. This is the plot, okay, as you get closer and closer. I don't have the function here. As you get closer and closer to this asymptote, you see it costs more and more to get an incremental additional removal. That is traditionally what was called the law of diminishing returns, okay? To get a little more removal takes a lot more money, okay? And that's where the asymptotic behavior comes into play. But this example, for a big multi-million-dollar company, that's chump change, okay? They won't say it is, but it really would be, okay? If you're a very small firm, that may be several employees, but, you know, for a big company, it won't. Okay, that finishes the application. That finishes the section 2.6. There is a checkpoint at the bottom of the page, as there is after every exercise. Oh, there was example 9. I didn't see this. Let's do example 9, okay? Let's see if I can find more white space. Okay, let's do it here. They didn't do it in the book. A rectangular page contains 48 square inches of print. This is not a very pretty rectangle, okay? Okay? 48 square inches of print. Okay, that's in the middle there, okay? The margins at the top and bottom of the page are 1 inch deep. Okay, top and bottom page 1 inch deep. The margins on the sides are 1.5. I haven't drawn this to scale, obviously. I should have read the problem first. But this is 1.5 inches. Okay, and that looks more like it, 1.5 inches. Okay? What should the dimensions of the page be to use the least amount of paper? Okay. What should the dimensions of the page be to use the least amount of paper? Okay? I can almost tell you the answer now, but we won't. We'll go with it. Okay? Now, you can't solve this analytically. You can solve it with a graphing calculator. I was wondering why I hadn't done this before, and then when I looked at this. You can do a graphical solution, or you can do a numerical solution, but you can't do an analytical solution. Not with the tools we have in our belts now. They'd have to give us at least one more piece of information. So I'm going to leave that off for now, but let's just see what the answer is. No, I was not quite accurate on mine. I forgot they had differing lengths on the ends, okay? But it's going to be closer to square than this is, okay? And as you see here, it'll be x is about 11.5 inches, and y is about 5.6. So I was way off. I thought it was going to be closer to square than that. But that's because you have the differing amounts on the ends. But you cannot do it analytically. So I'm not going to expend your time doing that. Okay, so let's move on to the vocabulary, the top of page 175. On 2.6. First, functions of the form f of x is equal to n of x divided by d of x. Okay? Trees, is it? Okay. Okay, I know you. There you are. All right, good deal. Functions of the form, f of x is equal to n of x divided by d of x, where n of x and d of x are both polynomials, and d of x is not the zero polynomial, are called blank blanks. Rational functions, absolutely. Number 2, when f of x is approaching either plus or minus infinity, as x approaches some value a, and f of x is going either to plus or minus infinity, and x is approaching a from the left or from the right, x equal a is a blank blank of the graph of f. So the function is either going this, or this, or this, or this, or this, or that, but it's approaching an infinity as x approaches some value. X equal a is called a what? It's not Veterans Affairs. Vertical asymptote, perfect. Okay? Number 3, when f of x is approaching b, that's the y function is approaching b, when x is approaching plus or minus infinity, y is equal to b is a blank blank of the graph of f. Horizontal asymptotes, you got it. Haha, okay, never mind. Number 4, for the rational function f of x is equal to n of x divided by d of x, if the degree of n of x is exactly 1 more than the degree of the denominator d of x, then the graph of f has a blank or oblique blank. Slant asymptote or oblique asymptote. Okay, homework exercises here. Do either 5 or 7 or both. They're both at Calc Chat, 7's at Calc View. Do any of the odds 9 through 15. They're all at Calc Chat, 15's at Calc View. Do any of the odds 17 through 37. They're all at Calc Chat, 27's at Calc View. On these next ones, I would do all 4 of these, 39 through 42. They're matching, so you can do them all fairly easily, but only 39 and 41 will be in the back of the book and at Calc Chat. Okay? Do either 43 or 45. They're both at Calc Chat. Do any of the odds 47 to 59. They're all at Calc Chat. 49's at Calc View. Now, these say they require the technology. I think you might be able to do some of them without it, but you can use it if you want to. Either 61 or 63, and they both should be at Calc Chat. And then either 65 or 67. They should both be at Calc Chat. Actually, 67 is slant asymptote. You don't need to do that if you don't want to. 65 you should be able to do. 69, a good applied problem. So very similar to the one we just did. And that would be probably a slant asymptote, so you don't have to do it, but it still might be fun to do. They're all fun to do. Okay. Page design, the one that we just sort of talked about there. 71's like that. 73's an average speed problem. They should all be at Calc Chat. There's a couple true false, 75 and 77. You can do those. They should be at Calc Chat. 79 is a writing problems. I don't know if it'll be at Calc Chat or not, but you can check it. You can do 81. That should be at Calc Chat. And then there's a project on the Department of Defense. If that gives you an idea for a paper topic, you can do that. The one back there that was writing, you might use that as a springboard for a paper topic, but I don't know that it would be all that useful. There was that was number 79. Maybe, I don't know. All right. 2.7, nonlinear inequalities, that wasn't required in our course description, so we're not responsible for it, so don't sweat that. Okay. Now, if you need more things to help you study for the test, there's a chapter summary starting on page 188, 189. That has, by section, various things about it, including some hints, maybe a few formulas or things you might use for section 2.1, 2.2, 2.3, 2.4, 2.5, and 2.6. Don't worry about 2.7. Okay? So you can use that. That might be helpful. Remember, you can bring with you at the test, which is Thursday, day after tomorrow, a formula and equation sheet. Anything you want to write down on a piece of paper, you can bring with you to the test. There's some review exercises if your homework is not enough for you, and these are also at Calc Chat. The odd numbers are at Calc Chat, so you could do number 1 if you chose, 3 through 7, any of those, 9, 11, 13 or 15 or both, 17 or 19 or both, or 21. Okay? Those are 2.1 and 2.2, 2.3, 23, 25, 27. 2.4, 29, either 31 or 33 or both, and 35. 37 and 39. 2.5, 41, 43, 45, 47. 2.6, 49, either any of the odds 51 through 57, 59, and then 2.7 you don't have to do at all. There is a chapter test at the end. Now, in the chapter review problems, I think, the review exercise I just talked about, all those answers are in the back of the book, but only the odds are at Calc Chat. Okay? The chapter test, all the answers are in the back, but Calc Chat is only the odd numbers. And you can do any of the numbers on this, 1 through 9. Okay? You don't have to do 9 if you don't want to, and even part of 8. No, all of 8, because those are irrational, complex numbers, and those weren't required, but you know how to do them. I think you, basically 8, 9, and 10 all involved complex numbers, imaginary parts. I think 12 would be okay to do. It may have some imaginary in it. 14, well, if you're doing Calc Chat, then just do the odds. 13, 15, and don't worry about 17 or 18, because those are the 2.7 that we skipped. Okay? So you have a few others there you can look at. There are some proofs given, and you certainly can take a look at those if you choose. Problem solving, there are some of those. You can use that if you'd like. But what we're going to do, and I needed to pull this up and out, is move on to chapter 3. Okay. All right. Well, it's not coming up. There we go. Okay. Now, obviously, we're not going to have time to finish chapter 3. So your last test, and here's what we're going to do for the final exam. It will be in 2 parts. The first part will be your chapter 3 test. It's going to be very short, not cover a lot of material, but of course it'll be very sweet too if it's short. Never mind. But that's going to be the first part. Won't take you very long to do it, I don't think. Certainly less than an hour. The second part will be the comprehensive part. And again, I'll make that very short. And right now I would say 4 questions on chapter 1, 4 questions on chapter 2, and 2 questions on chapter 3. Okay? So that will be your final, very short, more like a quiz really, but you'll be doing it in class. So you can take as much or as little time as you need on either part that you want to. If you can't finish in an hour and 50 minutes, which we're allowed, and by the way, I think ours is, I haven't seen the exact times, I'm guessing that's 8:30 to 10:20. I think it's probably when the final exam is scheduled for that Tuesday. If you don't feel ready for it on Tuesday, you can come anytime later. Just catch me either in another exam or, and by the way, this is the only test that's given in this room. All my others are in 255. Or anytime when I'm in the office, and you can take it if you don't feel ready, or if you want to just take Chapter 3 on Tuesday, finals week, and then, yeah. So you can do it however you want to, but you just need to have everything. Are any of you graduating this term? That you are, okay. You've got to have yours done Monday, Tuesday, or Wednesday, I think, because I have to have grades in for you before, because graduation's Friday, okay. So you don't have as much flexibility. Everybody else have to have the exam finished by Thursday, because Friday we go to graduation, so I can't be grading then, okay, or administering a test then. All right, any questions on that? I will be returning to everybody everything that's been turned in except your research papers, which that's not too many, okay, but everything will be returned to you. If everybody gets things to me sooner, you'll get them then. But if they don't, then you'll get them that Thursday before the final on Tuesday. I'll return everything. At that point, no one can make up anything else. So you have to have all your quizzes and tests done by Thursday of next week, okay? Including this test we have this Thursday. All right. So let's get started on the current slide. If I can find there it is. All right, now we've dealt with polynomial functions. What are those? Functions that only have exponents, positive whole numbers. That's redundant, but I'll leave it like that. Rational functions, which are ratios of polynomial functions. Now we're moving to two other kinds, and the first of these is exponential functions. So, oh, we've been dealing with exponents. Well, not quite the same way. And then from there we'll go to logarithmic functions. So let's start with exponential functions and their graphs. We'll first recognize and evaluate exponential functions with any old base A. 7, 14, 3, 2, 1, height, whatever. Okay? We'll graph exponential functions and use the one-to-one property. What in the world is that? That's not the same as a one-to-one function, but it's sort of similar. Recognize, evaluate, and graph exponential functions with a base E. Okay? Anyone know what E is? Say again? E is basically called the natural base of our number system. We say our number system is a base 10 system. It really isn't. It's a base E system. But E is an irrational number. 2.71, blah, 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 and goes on forever, a lot like pi, but different. Okay? And then we'll use exponential functions to model and solve some real-life problems. So first, let's figure out what an exponential function is. Now, I left off from before the term algebraic functions. So far in this text has dealt mainly with algebraic functions. They would include polynomial functions, rational functions, all those kind of functions are algebraic functions. This chapter will cover two types that are non-algebraic. First is exponential, second is logarithmic. These are often called examples of transcendental functions. We sit on the rock and go, no, that's the wrong time. But these are transcendental functions, not algebraic functions. So here's the definition. Now, in algebra, we had a power function that used exponents. X to the A, right? X raised to some power. That could be a positive power, a negative power, a fractional power, any kind of power. Okay? But it's raised to some fixed power. An exponential function, though, is sort of a flip-flop of that. F of x is A, some base, raised to the variable power. That's very different from having the variable here and the number there. That's a power function. This is now an exponential function, which is the base here is the constant, the variable is the exponent. Now, here are some requirements. This A is always positive. You never use negative A's for bases, ever. Okay? But we also never use 1 as a base, because that would be a very boring function. 1 to the x power is 1. You know, flat line. never changes. So we don't use that. So we only use a's positive, and those could be not small numbers like 0.3, or something like that, but they couldn't be 1, or anything greater than 1, 7, 3, 1.2, anything like that. But x is your variable, and those are always real numbers. We're not going to deal, at least in this text, with complex numbers for the exponential functions. Okay? The base a is equal to 1 is excluded because it yields the function f of x equal 1 to the x, which is always 1. Always 1. Notice the sound effect. Okay, never mind. Okay, that constant function is not an exponential function. You have evaluated a to the x for integer and rational values of x. Okay? Now we're going to let that be a variable. We know that 4 to the third is 64. 4 to the 1/2 is 2. Yeah, we can put numbers in there. That's really easy. And we're going to be putting numbers in. But that's for fixed numbers. We're going to let it be a variable now. However, to evaluate 4 to the x for any real number x, you need to interpret forms with irrational exponents. Not just rational numbers, irrational exponents. For the purpose of this text, it is sufficient to think of a to the square root of 2, where square root of 2 is approximately equal to, because this is an irrational number itself, 1.4142135 blah, 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 blah. It keeps going forever. They just truncated there. Okay? As a number that has successively closer approximations. Okay? You could approximate it by a to the 1.4. Or a to the 1.414, or a to the 1.414. These are all rational numbers, okay? But that's an irrational number, and you can just keep going until you get all those numbers out there. You'll find it changes very little after a whole bunch of new digits, but it's still just an approximation. All right. Why they do that, and all the books do, really sort of a off-the-wall type thing, but your calculators will do it with no sweat. So this was back in the day before calculators. All right, so using your calculator, evaluate each function at the indicated values of x. So pull out your calculators. If you don't have one, look on with a neighbor. Cell phones will work. Okay, I believe you can do this on a cell phone. You'll have to turn it sideways, but try it anyway. F of x is equal to 2 to the x. Do it when x is equal to negative 3.1. Now, does anyone want to make a guess of what value that will be? That would be, let me get my pen back. While y'all are punching it in, see if you can figure out a way to do that. Okay, that would be, I'll put approximately equal to 2 to the negative 3.1, which would be 1 over 2 to the 3.1, right? Y'all remember that, right? Okay. Now, that's pretty close to 2 to the 3. So these are exact. This is approximately equal to 1 over 2 to the 3, which is 1/8. Okay? So it's going to be approximately 1/8, which your calculator will read that 0.125. So you're going to be something pretty close to that. Did you get something close to that? Anybody?
That's 0.116.
Okay, you got 0.116. Is that? Huh? And it goes a lot longer than that. But so, see, it's not far off from that. Okay? It's a little bit less because the number there, 3.1, is a little bit more than 3. So your denominator makes it a little bit less. So yeah, that's what that one is. Okay, how about f of 2 to the minus x when x is equal to pi? Well, 2 to the minus x, let me bring it down here, is 1 over 2 to the x, right? And when x is equal to pi, that is 1 over 2 to the pi. And you can do that on your calculator if you want, or you can approximate that to be 1 over 2 to the 3.141. Yeah, It's almost the same number. It's probably going to be a little bit less than this number. 0.115 maybe? I'm guessing. I don't know. Huh? 113. That makes sense. 113. Okay? So you see what it's doing for us. Okay? Let's do another one here. Whew. F of x is equal to 0.6 raised to the x power when x is equal to that. So it'd be 0.6 raised to the, you could put it as the 3/2 power. If I were doing it on my calculator, it'd be 0.6 to the 1.5 power, because 3 divided by 2 is 1.5. That would be easier to enter on your calculator. See what you get there. 465. And so it goes on and on and on. Okay, right? Okay, so you see how to evaluate exponential functions. Given an x, yeah, plug it in, plug it in. Okay? So that's evaluating an exponential function. Okay? Now, I'll erase my scratch here so you can see how they do it. When you put this in, now this is how they suggest, if you have a calculator with different syntax, you'll have to do it the way that your calculator is. For sort of standard calculators now, you do the base 2, the exponent is the caret key. Now, if some of you don't have a caret key on there, you may have a key that says a to the b. Then that would be the same thing. Those are older calculators. Okay? But if you're using the caret key, then to get the negative, do not use the subtraction key. Use the key in parentheses, the negative in parentheses. The subtraction key doesn't work for this kind of application. This is the negation key. In the old calculators, this was a plus-minus key. Okay? And then you enter the number first and then the plus-minus. With this key, you enter the minus first and then the number. In the old calculators, it was CHS key, change sign key. You entered the number, then you changed the sign. Okay? But in the more modern calculators, those that will have the caret key will usually have the negation key, 3.1, then press enter, and you get your answer. 1.116, 0.116629, blah, blah, 1. It goes on and on and on. Okay? All right. Alpha pi, when your function is 2 to the minus x, they should have put that function in here, but they didn't. 2 to the minus x, alpha pi would then be 2 to the minus pi, which is almost the same thing. Pi is 3.141, so it's going to be a little bit less, and sure enough it is, 0.1133147. So very good on doing that. Here we were doing an irrational number, but you see most of your calculators have that in your calculator. Now that's a round-off value itself, but it's rounded to probably something like 12 digits, so you're not going to be able to tell a difference most of the time. And then here's another one, alpha of x equal to 0.6 to the x, and if you're doing 3/2, now here's one way to do it. This is an awful lot of keystrokes, but you put the 0.6, you don't need to put the 0 if you don't want to. Caret key, and then they're doing it this way, open parentheses, 3 divided by 2, close parentheses, then hit enter. So it's so much easier to do 0.6, caret key, 1.5, enter. Okay, you don't need parentheses, you don't need division. If you go on and do that division in your head, which you can, and that gave you 0.464, 7, blah, 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 blah. Okay. So any questions on how you evaluate exponential functions? You'll need to know this because you're going to be graphing them, and you'll need to be using your calculator to enter that. Everybody see how to do it? Anyone can't do it on your calculator or a phone or whatever? I can help you with it. See, y'all are better at that stuff than I am. All right, so there was example 1. Now, let's look at graphs of exponential functions. Like I said, you will need to be evaluating some, so we'll do it. On the same coordinate planes, let's sketch the graph of each function. Okay? Let's first do 2 to the x. Okay? I know already this is always going to be a positive function. Okay? But we could have x values that are not positive, so let me change that. Okay. Okay. Move my y-axis over to here. Okay? So, I'll tick off a few points. 1, 2, 3, 4, 5, 6. I'm not going to need that many. 1, 2, 3, 4, 5. Not going to need that many. I'm going to need every one of these. Okay? And more. Okay, give me an x. 0. And what's 2 to the 0th power? Second? 2 to the 0th? Anyone say something? I thought I heard someone say something. 2 to the 0th. 1. Exactly. Okay? Anything to the 0th power is 1, except 0 to the 0th is undefined. Okay? X to the 0th power is 1. 3n to the 0th power is 1. Anything to the 0th power is 1. Okay, give me another x. 1. And 2 to the first power is 2. Okay? Give me another x. Second? Negative 1. 2 to the negative 1 would be? Second? 1 over 2, which is 1/2. Okay, give me another x. 2. 2 to the 2 is 4. I can put that one on here. Another x? 3. That would be 8. 1, 2, 3, 4, 5, 6, 7, 8. That's as high as we're going to be able to go. Okay? But notice here, it is increasing and increasing incredibly fast. Okay? How about a few more negatives? Negative 2. 1 over 2 squared is 1/4. Okay? 1 over 2 to the third is 1/8. 1 over 2 to the fourth is 1/16. You know, then 1/32, and then 1/64. It's getting closer and closer to 0, but never goes negative. Ever. Never reaches 0 either, by the way. That's typically how an exponential function looks. A few keys. At 0, it's always 1. Okay? And then it goes up or down from there. Now let's do g of x in a different color. What color you want? Second? Blue. Okay, light or dark? Light. Okay, there's our light blue. Okay? Give me an x. G of x is equal to 4 to the x. 0. And what would that be? 1. Perfect. Give me another x. 1. That would be 4. I think that's it right up there. Yep. And then another x. Negative 1 would be 1 over 4, right? 4 to the minus 1 is 1 over 4. That would be 1/4 right there. Okay? Give me another x. Second? I can't hear you. I'm sorry. I can't hear you. Yes, it's going off scale. You're absolutely right, because 2 will be 16 off scale, way up there. So it's going up even faster, and guess what? It's flattening out even faster here. It stays halfway between the previous one and that one, all the way out. So you see, this is what higher bases will do. They go up faster on the positive side and go down more quickly, but still get flatter sooner on the negative side. Okay? And if you had, what happens if you put a 1 in there for your base? You don't. The base can never be 1. Remember, that was the rule. How about negative 3 for a base? You don't. We never use negative numbers for bases. Okay? But if you use 0.5 for a base, whoa, things flip over. Because then, when you do 0.5 to the minus, that's 0.5 is the same as 1/2. That would be 2. Then you're going like this. Okay, so that's what exponential functions do. And I'm afraid we are basically almost out of time, aren't we? Okay, so we'll begin next time with, oh, let me just show you. Here's how they did it. They didn't use different colors, but you see they got the same results. They did a lot longer Y scale, and that's what their 2 functions look like. Okay, notice both graphs are increasing. Moreover, the graph of g of x increases more rapidly than the graph of 2 to the x. All right. All right, we will begin next time with example 3. Okay, yeah, and that's what I've got marked already. So we'll begin next time with example 3. All right, homework exercises here. I think you got enough to do a little bit. Okay, I think you can do any of the odds, 7 through 11. They're all at Calc Chat, 7's at Calc View. And we'll hang off the others for later, okay? Now remember, Thursday is a test on Chapter 2, okay? Bring with you a formula and equation sheet. Anything you want to write on a piece of paper, front and back, as big or small as you want to write it, you can bring that to the test. Okay, bring your scratch paper calculator. I'll have some graph paper because you have at least one graph, I think, on the test. All right, good deal. And I have to have your quizzes in before you can take your test. So if you haven't done your quiz, please get it done. Get it to me before the test, either today, tomorrow, or Thursday morning before you take your test. Okay? If you don't have it finished, come and finish your quiz and then take your test. Okay? Good deal. Have a good couple of days. We'll see you on Thursday.
Hey, look.